30 as well. All right, so last time we talked about some general stuff about modeling, and what kind of behaviorally these models can bias. And today we want to continue and also expand or like talk more about internal interpretability and looking at these models, introspecting them, and seeing what we can get with that. Any questions from last time? I'm gonna scroll through the slides if something rings a bell. So we're in informative modeling language as informative imitation world. These are the models that we're looking at. Basic modeling, basic stuff. This is a slide I didn't show you last time. So this is how you can model language change in iterative learning tasks. So English aspiration rule, for example, when you have the S condition, it's stable throughout generations, but like the S condition gradually moves towards no rule. And so that's one of the results we had. Then we were looking at this monosemanticity, figuring out which latent space variables represent what, and how to causally force them in the output to see a causal effect of what you're interested in, which is a very powerful tool because it allows us to do all sorts of work tests on the models. We saw word learning, which is a big deal. So how do people learn words? How do human babies learn words from enormous search space, right? If you think of a child, needs to learn to basically pair meanings with the form, and it has to hear, look at everything it hears and all possible words. So it's a very, very challenging search space. And then we talked about productivity, we talked about new words, and then how to test internal representations, how the bit structure, right? So the bit codes, bits are compositional. Sorry, the binary code are compositional, made of bits, and how models take advantage of that to learn compositionally, phonetics stuff, and then a few use cases of reduplication, more harmony, all the things that we can model. And then we're pretty much here we're going to look at the models more closely in a neural way. But are there any questions before we get there? All right. So so what does the model do, right? So it needs to learn to transform some extremely small duration. It has a very small vector of 100 variables onto real data informatively. And it does so with a few steps. So here you'll see the latent space consists of a bunch of code variables which contain the information, or like we model information in terms of these codes. Okay, later on next week, Stefan will introduce how these codes can actually be referential meaning if you add vision to the models. But these codes get first, they get appended to the rest of the latent space, the Z space. And then the first thing that the model does is the so-called fully connected layer, FC layer, where each of these 100 variables is fully connected with each of the dimensions in the fully connected layer. And those dimensions are 1024, basically time series, tiny time series of data that have only 16 points. So the dimensionality of each time series is only 16 points. And in the fully connected layer, we happen to have, I mean, this is taking off the shelf. Again, I think this still goes back to DC again in 2015. We have 1024 waveforms, the tiny waveforms, tiny time series data. You can see here, right? So each latent variable, each of the 100 latent variables has a weight to each of the 16 points, and altogether there are 1024 of such series of time series data, and those weights are learned. Okay, plus there's bias, of course, during training. So this is the first transformation that happens, and so each basically each latent variable will have 1024 times 16 weights that are learned. And this constitutes the so-called fully connected layer, which then gets passed on to convolutional layers, which have the filters, right? So filters, it's not, this part of the network is not fully connected anymore. It's convolutional filters, because if it were fully connected, that would be extremely computationally complex. So convolutional neural networks were proposed as a solution based on human vision, where you have a filter that scans through the input, goes through the input, you perform multiplication, and then each layer has a number of filters. And what is crucially important is that we're not as much interested in those filters as most computer scientists were, or most vision people were. In speech, it's really actually more informative to look at the outputs of the filter. So each fully connected layer gives you 1000 time series of the dimension 16, and that goes then, this is called a reshape layer, and in the collab you'll see all of these layers named like this, and that gets transformed into 64 by 25. 64 is the dimension, right? So you're upsampling, in a sense, you're upsampling in a generator. But this first layer has 500 filters, and each filter is probably doing something. And filters are learned, right? So filters have weights, and they're learned weights. But what we're interested in is the output of those filters. So the filter gets an input. It performs, you multiply that input with your weights, and after some activation, it spells out an output, which is a slightly larger time series data. And so on through the layers onto the final layer, which is then the actual output. So there's really interesting work by Bruno, who is a student here, and a student also at Brown, who's looking at linguistic representations in this first fully connected layer. This is basically the first step between symbolic representation, symbolic classification, basically one hot or binary code encoding of words or sounds into a kind of semi-physical already property of the speech output. And if you look at the fully connected layer, I think this is weight matrices. And so, this x-axis can already be understood as a time series, as temporal dimension. And basically you can slice these abstract representations and show that as you take this slice and send it through convolutional layers, you will get, say, something like a vowel, right? So you will get linguistically valid representation of sound vibration. And so that's really nice, because a lot of the times GAN's GAN kind of training has been described as non-temporal, but this work shows that basically you can think of the x-axis in a fully connected layer as a time representation of the time, and it doesn't have to be that you have to send your entire dimension through the convolutional layer, even if you just take a single column, a single point out of 16 points, you will get essentially a structure of a speech sound. And that's really nice because you can actually take a single column and generate, and you'll get a single sound, like a vowel I or a consonant S, and so on. We'll get back to the fully connected layer when when I'm gonna try to convince you that there's something very close to what formal linguists conceptualized of as merge operation happens in this layer. But stay tuned for that. Okay, so from this layer, then the signal travels through convolutional layers. And as I mentioned, each convolutional layer has dimension, right? So this is the convolutional one. It has 64 now data points. And it has 500 time series data. Here, time series is color coded, so you see the higher values of the air pressure. Air pressure. A representation of air pressure will have brighter colors, but this is not very interpretable. Okay. So this is just the raw feature maps, but we are interested in so-called feature maps. It's the thing that comes after the filter for each layer. And we described this I think from our 2022 paper. And then second layer, third layer, you see the interpretability of these raw feature maps is not quite they're not quite informative. As much as the some averaging over the mean time domain, which really gives you a summary of what each layer is doing, right? Again, this figure shows you that purple is the vowel that the model generates, and here you have a frication noise and the silence of the stop and the burst. And so the layer before that is orange, the layer before that is green. And so you can see how the network cumulatively really kind of follows this frequency, follows the output. And you can basically analyze how step by step the networks create this signal. Okay, they start with low. Okay, so we saw in the structure of the network. Of course, there's a Nyquist frequency at each layer, right? So at this layer, you can only encode. You can encode everything below 8,000 hertz, which is basically our speech. Here it's below 2,000 hertz. Here it's below 500 hertz, right? So when you look at frequency encoding, the model needs to encode can only encode lower frequency stuff. The deeper you get. But I showed you last time, the model basically switches from frequency following type encoding onto absolute values encoding when you get too high in terms of when the frequency is too high for Nyquist frequency at each convolutional layer. And that's something very interesting because the brain does something similar, but we won't talk about that during this class. Okay, so again, a vowel, fricative, you can basically analyze each layer, and you can then also see, right? Remember, we were taking a single value and stretching it to extreme values to see the underlying effect of each monosemanticity encoding phoneme. And so you can basically, in that way, you can kind of causally follow how something like an S gets encoded through the layers, right? So this is the fourth layer, third layer, second I skipped for some reason, first layer, right? You can only see traces of acoustic envelope and not much else. Again, a disyllabicity, so a model forces, well, you can force reduplication in the model. You see the reduplicated syllable starts appearing here. And actually, it's interesting. It looks like the reduplicated syllable gets the reduplication gets here is probably the nucleus of the non-reduplicated syllable, the first syllable of the non-reduplicated word, and it appears that the duplicative syllable takes that first part here, and the rest, you know, that some sort of silence of the consonant gets introduced, and the rest is like here. But you can follow that process throughout the convolutional layers, and you see, you know, here there's almost everything is still encoded. Here, you know, you get a little bit more abstract. This is the second layer. Third, more abstract. Here again, only the envelope is encoded, and not much else. But you can still definitely see the envelope, which is going to be interesting for when we get to the brain in very short time. Yes.
Hi, can you explain the axis?
Oh yeah. So this is time series, right? This is waveform. So time. Z is amplitude. And here is basically generation of waveforms. You know, you just generate each waveform with the value of Z of C that encodes reduplication, either negative or positive, right? So here I'm saying I'm saying very strongly be a reduplicative output, have a reduplicant in the output. And here I'm saying be a base, don't have reduplication in the output.
How do you get these results from the layer?
Yeah, that's a great point. You just at each layer, I think we have a formula here. At each layer, you average over all feature maps. So you take, so each, okay, I can show you like this. Here are the feature maps or outputs of each filter in, I think, the first layer. You average over all these feature maps. You see individually, they're not as interpretable. I mean, they are to some degree, we'll get there, but individually, each filter does something differently. And actually, one interesting thing to observe here would be what do these learned filters actually pay attention to? What do they do in terms of acoustic processing? So you can imagine, you know, populations of our neurons probably are attentive to different acoustic things. They're trained to do that. Or we learn, you know, they learn that. And so, so each probably population does its own thing in processing, and then it, you know, at some level, it gets sent to a higher level for further processing. But if you sum these over, you get these basically time series for each convolutional layer. It's, I think, very, very informative. And then, you know, a crucial step for when we do this with neuroimaging. Why is averaging so appealing here? Because what you're doing essentially is the same as neuroimaging is doing. So neuroimaging, especially, you know, more crude versions of it, like EEG, are nothing other than averaging electric activity in time domain, right? So, so there's a similar process you get to the signal through. You can do some interpretability on individual features if you're interested in that. We have a paper. This is our TST and TASLP. But at least at the lower layers, the averaged feature maps give you a very interpretable output that you can use for all sorts of purposes. Yes.
Following up on that, so you're saying, like, for the reduplication case, you weren't scaling like a single feature, but scaling the average?
No.
This is a single feature.
So, okay, feature is a loaded term. So this is taking out of 100, I'm taking only C2.
So this is the original encoding.
Yes.
These are the zeros and ones.
Yes. And then this is plotted waveform.
Got it. So you're taking the, originally, like all the words are encoded as zeros and ones, right? But suppose you.
Plus 100 random variables that give you variability and encodes all sorts of other linguistically important things, yes. So you have 100 latent variables at the very end of the generator, or at the very beginning. Yeah. And then, at the end you have waveform.
So you still have your zeros and ones, but then those are connected to this first layer.
Yeah.
Okay. And so this is one of those values in the first layer.
These are all feature maps, i.e. the waveform that is about 4,000 points that comes at the end of each filter at the most shallow layer, averaged over all feature maps, right? When C was 2, when that single neuron was 2, and then when it was 1.5, and then when it was 1. So basically the idea is you get understanding of how this last first feature, latent space variable, what kind of effect it had not only in the final waveform, but throughout the layers. But the crucial part is we're visualizing averaged feature maps. And they contain a lot of information, and individually they're also interesting to interpret.
So visualizing the average feature maps.
Yeah.
But we're still talking about like the first layer.
Yes.
That's what's important.
Yes.
You're saying that layer actually like learns something that's linguistically.
Yeah.
And and I was expecting the visualization would be like the output. But you're not saying.
This is the output.
Yeah, okay.
Yeah. Output, layer before that, layer before that, layer before that, layer before that. And then the only thing that is before that is a fully connected layer. And the only thing that is before that is the, symbolic world.
Do we want to, like, how much do we want to interpret that first layer? So we have our zeros and ones, and then we have our first.
Fully connected layer.
Fully connected. Is that C2, that's in the fully connected layer?
No. C2 is in at the very beginning.
Exactly.
So here is C2.
Yeah.
Yes.
Exactly.
Here's.
Yeah. So how much do we want to interpret that first?
A lot.
Yeah.
I think.
How much do we want to interpret that as being something like the phonological encoding of that word? Is that?
Yeah.
So do you want to say that like what happens later on in the convolutional layers is like not that linguistically relevant?
Yeah.
And that these kind of like 100 values,
Yeah.
that's where our phonological representation.
So this is phonological representation.
Yeah.
And here is probably all information you need in the phonetic encoding. This is actually, we started looking at this layer relatively late. This is work with Bruno. And really cool stuff. And then this is then kind of a more mechanistic execution of what is here. So these weight metric matrices are very interesting to interpret. But also you can, it's if you do then early brain processing, these will be interesting things. So you can think of, brainstem. Well, when we did work, the closest signal to the brainstem is here, and the closest signal to ECOG is here. And of course, we don't have monosemanticity here. Or like there is actually some neural work, interesting, very recently they were not doing single neuron probes, but there is. So when it's warranted, a surgeon will open your skull, and in damaged tissue will put a probe, a very tiny probe that records neural activity at a single neural level. So maybe there's something there, and this, I haven't really conceptualized this yet in terms of brain, but there is a lot of information here about kind of word structure. Actually, with in Bruno's paper, we have evidence that, you know, a articulation happen here, stuff like that. You know, well, I'm not talking about motor planning yet, because we get to this in the second part of the class. We'll talk about articulation. This, in a sense, is not a very realistic representation yet, because I'm making a shortcut. What kind of shortcut I'm making? I'm generating waveforms, and we're not waveform generators. We are muscle control generators. But that is a way more difficult thing to interpret, as many of you in the audience know. Oh, we'll get there. Okay. Yes.
Have you considered modeling the muscle activation and vocal tract and all that kind of stuff in other people?
We'll fast forward several slides to this model, which is the latest. So the generator does not generate waveform anymore, but EMMA channels. EMMA channels get fed into pre-trained physical model, so-called EMMA to wave, which has nothing to do with cognition. How our air that gets sent through the resonant chambers and vocal folds get transformed into a vibration, a sound pressure vibration, that has nothing to do with cognition. But it was a very difficult problem to do. Taking EMMA and turning them into waveforms pre-neural revolution was near impossible. I mean, there are German labs who try to do it analytically, but it was very hard. Now we just take a model that is pre-trained from that task, freeze it during learning, and now my generator needs to move the 12 EMMA channels plus voicing, because EMMA doesn't have voicing, into waveform. That waveform needs to goes to the discriminator, which forces the generator to imitate based on what it hears. But this now becomes a really difficult problem. Now the generator needs to do something completely different. It needs, and it only, so when I was doing this modeling, it occurred to me, and maybe people have already know that, but like sound production and perception are two radically different modalities. And in a sense, when we talk about sign languages, we talk about them about different modalities in sign languages. Yes, in perception, that's different modality, because you perceive the visual input versus the sound input. But in production, in a sense, it's very similar. It's muscle control, right? And so the generator needs to do something very different. So it needs to control EMMA channels such that the sound input that it has no access to will approximate what parents are doing, right? So if you think of a child, it needs to learn to move articulators such that the sound it produces approximate parents. And there's a lot of articulators we don't see. I mean, there are some that we see, like lips. And then it needs to do so informatively, such that this waveform will carry a message. And then we're showing that this learning works. It's a little bit more challenging to then have this Q network be evaluating timid, because this EMMA to wave is trained on a single British speaker, but that's ecologically valid. That's ecologically good, because we have only one articulator, right? But this British speaker needs to learn timid data. And it's, it becomes a highly challenging learning objective, but still learning happens. So you have clear words, words, codes per word, words get learned. We haven't really looked a lot into how articulators get learned, but they do get learned. And then you can compare trajectories. So here's a trajectory for suit, the word suit, I think. No, wash. Um, and you can see for each channel, you can plot generated, which is green, and real, which is blue. And you can see similar trajectories when the model is searching through the space of motor actions so that it'll generate stuff that it hears from the environment. But there's a lot that to be done here. So we have Emma, now you have Emma data. You have a whole generator of Emma data that nobody has actually looked at yet. So what happens here is we haven't had a time to look at, or even in the fully connected area. It would be interesting to see if you can see some sort of high-level representation of gestures inside this network. And then you have a lexical classifier, and then the discriminator, and there's Bruno has some work on the discriminator and how it learned phonotactics. So now you have this system where a lot of these things that we've been studying in production can also be studied. But we need to do more work on analysis. So I jumped to a different topic, but that's fine because it was good that we did that. Okay. Any other questions? Yes.
I guess I'm wondering, whether the architect people have played with the architecture to see like how many hidden layers you need, what is
Yeah.
shapes of these things.
Yeah, no, for sure. We have some work on that. You can reduce dimensionality by a lot. Like you can work with 25 latent variables. Actually, Bruno's, I think, in the archive paper we show that even this fully connected layer can be way trimmed, and you still get interesting learning. And Stefan will talk about next week. We'll talk about all the tricks, well, all the things you can do when you add vision, or if you add a parent. We'll add a parent to the mix. Okay, this is not the most realistic. So this is basically just child internally, as if it had no interaction with the parent. Now we'll add the parent, but you have to be careful, right? So you have to think very carefully through which backprops you're allowed to do, right? Because my caregivers did not have a neural connection between my brain and their brain, right? So you cannot have some things. So it's actually a lot of fun when you see how these are communicating and then playing games. So we talked about this, right? So the same interpretability as you have for the generator, you can do on the discriminator. But the nice thing about the generator is that you can do the so-called extreme values, right? So instead of 1, you generate with 15. You cannot do that in the reverse direction. So you have this causal effect of a single neuron, and you can see it because you're generating with extreme values. Whereas in the perception direction, they're like there were some people trying to do convolutional pass in the other direction. I think it's called deconvolution, but it's not as successful. So you can see more clearly in the generator, and it's always nice because you can always validate whatever you observe in the Q network. You can validate with the generator, but you can send hundreds of words through this network, and this is actually more valid, ecologically valid. When you do brain comparison, which we're getting to, of course, almost all the brain work is on perception, not production. There's very little on production. We have some cool data on production, but it's so messy that nobody wants to touch it. So you can just take a bunch of input to the Q network, and then, you know, understand each layer, and then understand final classification. And so this is what we talked last time, right? So now this is the final convolutional layer, so the deepest layer. And the words are represented with these shapes. You can see that because, you know, you take library speech, you send 500 library speech words of year, instantiations of year through the Q network, and you see that the Q network represents different words with unique shapes. And one thing that is really, I think, there's a lot to be done in interpreting this are these how words get basically classified, what the network is paying attention to, and how it's doing that. And I mentioned these bursts that get amplified, and you see how I'm getting to the more brain stuff, because if you look at what brain does, it's very attentive to this sudden movements of amplitude, and this is probably a similar process where the brain then, you know, has population of neurons that are attentive to various different inputs, and then, you know, gradually builds a classifier that takes information from various different sources, and then at the end of the day classifies. And so I think, you know, for dynamic field theory work, this would be interesting to see how these activations happen, and whether they follow some of the laws, if you're taking Jason's class. So this is the Q network, right? Almost same architecture, but reverse. And at the end of the day is classification. Well, this is actually the discriminator, which needs to figure out the reality of the output, but the Q network is essentially the same. We talked about this, so for neuroscientists, this is actually interesting venue to explore, because, as I mentioned, this level encoded is interesting. You can also, you know, plot differences of word shapes and understand how network encodes maybe phonemic structure. But you can read about this in the paper. So I want to spend some time on auditory brain stimulus. Well, on the brain work. So there's a growing body of literature that compares these neural networks with the actual brain processing. And you might have very diverse opinions on this topic, because some people say that it's a horrible thing to do because neural networks have absolutely nothing to do, well, or today's neural networks have almost nothing to do with the brain, and it's a horrible science if you do that. And there are some people that say, well, take any transformer, find a linear mapping between some layer in the brain, and then you say, well, basically transformer is the brain. I mean, I'm exaggerating a bit. One nice use case, you know, to contradict those people, well, maybe not, but like, you'll be the judge. But you can take MRI scans of the brain, fMRI, and use a GPT-2 to predict sentences that people are imagining. Now, it's not so clean because you have to prompt, you have to prime people for those sentences, but the proof of concept is there, and that was the GPT-2. There was Alexander Hoot's work. That was GPT-2 work. I can imagine, you know, with better models, it can be better. But you can think of, you know, the brain learns language and it has some mapping. And a large language model learns language, it has some mapping. Probably those are not completely distinct. I mean, there's this hypothesis that any kind of system will converge in the same mapping given an input. And you just need to find the rotation. So between these two systems, and you find that, you can basically generate from one to the other. But again, those are more engineering colored people who work on that. And what we want is to be more, interested in science and mechanisms. And so the idea is that we don't use transformers because there's no bottleneck, they're less interpretable, they're very difficult to interpret. Second, we avoid linear transformations, even linear transformations. So I want to understand, is there anything raw in the data that I can compare or like interpret in terms of the brain? And so in that sense, this is good because the vast majority of brain work uses linear, uses some extra post-processing to show you similarities. And we try to approach this from raw, just raw comparisons. And so I told you about Christina's work. So when we hear sounds of language and other sounds, the membranes in our ears vibrate, the cochlea's liquid carries those vibrations, and that gets transformed essentially into electric signal that travels first through the brainstem in the cortex. And what you can do is you can catch the electric activity in the brainstem as you're hearing the sound of language. So I mentioned, people started with clicks and pure tones, but you can send something like a synthetic ba syllable, and play it 3,000 times to 15 participants and measure their electric activity. Of course, you average over all the trials, but you also average over, you average over all the trials. And these are the 15 participants. And if you average over 15 participants, you can basically see the F0, and you see the some form and information, especially low frequency. You cannot see anything which is above 2000 hertz. There's just limitations, but there's all sorts of interesting linguistic activity you can do with this. And so here are English and Spanish speakers, and they listen to ba sound, and the first peak you'll see here is the attention to the burst. Okay, so this is peak 1, and then there's peak 2, which is like during the VOT, and then you have peak 3 that represents the first vocalic pulse. And you see that all peaks are aligned between Spanish and English, except for this first peak, where Spanish speakers hear the ba syllable, hear the first period of the ba syllable, no pre-voicing, a short VOT plus 10 milliseconds, as slightly later than English speakers, right? So here's a mismatch. This is from Christina's work. Slight mismatch, and that correlates well with behavior. So, if you play a continuum, they switch at some level, and the Spanish speakers will switch later than English speakers. And so first thing that we try to show is that the most shallow layer actually does something very similar to the brainstem in what it's encoding, and in a very raw form, right? So if you take this exact same syllable and pass it through convolutional layers, or if you do it with the generator as well, you take approximation of that syllable. You can force the generator to approximate this syllable, so it's the other way around of saying the same thing. Well, it being the same thing. You get these feature maps, right? You're familiar now with feature maps. They're raw activations, and the first layer, there are about 64 of them. I think there's 64 time series here. And you see each layer, each feature is doing, well, some features are doing similar things, and other features are doing other things. But like cumulatively, you can sum them over, and you can see this relatively similar. I mean, this is the most similar you can get in the brain, in raw brain comparison. So, the first layer does encode probably similar information as the brainstem still preserves. And then you can train a model on Dimex and a model on Timid, mimicking Spanish and English speakers. And you can measure then if there are like similar peak differences, and we find similar peak differences. So in the Spanish model, the peaks were slightly, there was similar encoding and in peak latency as in the brain. And we replicated that twice. So we did 2 experiments. But the point is that you can test all these predictions about how the model will hear, or like how the model will encode sounds internally, and compare that to the brain in the raw form. So there's a lot to be done here. For example, you can test sensitivity period. You can test whether music. Christina has this interesting paper where she shows that musical processing helps tone perception in Mandarin. So you can train a model with music and a model without the music, and then you can train. You can see if the model has sensitivity period. Like if you train an English model that has no tone encoding, does at some point the model perform worse on brainstem encoding and so on. So there are many test cases that you can make with this model. So the proof of concept is there. And we have some really even better data when we move to ECOG. So electrocorticography is a different brain imaging technique that looks at your cortex. And we're showing that there are like really nice similarities in encoding between the cortex and third convolutional layers, where different filters actually are doing similar than different populations of neurons where they're attentive, or they're learned to be attentive to various different acoustic inputs. But that's the preprint is coming hopefully out soon. But that's roughly the methodology, and a ton to be worked on as well.
Say a little bit more about the reporting itself. You call it EEG,
CABR, yeah. So you have 4 electrodes. You don't need more. But crucially, and some companies are now phasing out.
EEG electrode.
Yeah. Some companies are phasing out the high sampling rate. So the crucial thing is that you're sampling with 20 kilohertz, because you want to catch the signal earlier than it could travel to the cortex.
The signal that you're showing, that's just the measurement in microvolts
Yeah.
across the 4 sensors.
Yeah. Oh no, that's actually artificial microvolts. Yeah, that's microvolts.
Okay. And so, and then we're interpreting each of the peaks.
Yes.
As linguistically relevant.
Well, not for everything. For example, you cannot study fricatives with this.
Right, but then, yeah, of course, yeah. But the third peak, that's where we were zooming in.
Yeah, this is the first vocalic period.
Okay, and then we're relating that to a difference in BOT processes?
Yes.
Okay, and we do that because of the time force of it,
Correct.
that's around in time. So the samples here,
Time, yeah.
so this is at 20 kilohertz.
No, because you have to do a lot of downsampling.
Ah,
Yeah.
okay. So this is occurring.
This is a whole vowel.
Okay.
By the way, there's one interesting thing that I've always wanted to do. So I don't have, I in the paper we have superimposed this syllable on we time locked it with the burst. And here you would see, it's in the paper, it's really neat. You would hear, vocalic periods, and then you would see silence. And there's some vocalic periods after the silence, which is really interesting. So
there's a delay. because
Yes,
what
yes,
you mentioned at the
yes,
points than
yeah,
the actual.
yeah.
That there should be some delay. I mean,
Yes, but I think some behavioral thing about vowels can be explained with that delay.
Oh.
Yeah, anyway, so that's
So,
a
but how, if
transgression.
you go back to like, how are we interpreting like this delay in the third peak? Like, so what is it? So what do we say? You said it correlates with the behavioral response, but what behavioral response?
Well, that you hear, okay, so a Spanish speaker would hear this, so as English would hear this as a voice stop, right? And it would be kind of prior to hear it, to hear the first period earlier, because it's mostly encoding sound as the VOT duration as the relevant cue, right? So I think that's the reasoning. English speakers hear it as shorter, and you have this, and then that relates into the behavior. Well, you can switch over if you just manipulate the VOT duration. You can switch over faster if you hear it faster.
So the Spanish speakers, would they also hear this as a voice stop or as a voiceless stop? Spanish listeners. You said can be.
Yeah.
It's a VOT.
Yeah, well, they're probably not as attentive to VOT, right? They're probably looking for other cues. So it correlates with behavior, and I think they can do you can do individual level correlations as well. And Alan Yu took this work over and looked at individual variances, and he has this idea that a lot of sound change variability can be explained with these encodings, and it's not only VOT. I mean, this is just one example. You can look at frequency following response of Mandarin tone. You can look at pool distinction, all sorts of things. And I think it's interesting because it suggests that phonology is encoded very much earlier than we thought.
Well, that's what I'm trying to get at. Like, I see in the data, like, I don't fully understand the interpretation of the data. So I do see that the peak that is maybe roughly in the area of the onset of voicing or during the aperiodic energy, or that's third peak, right? This is roughly in the area of something, during the DOT or during the onset of voicing, roughly in that area, right? Or maybe we could even be more precise, but it's at least roughly in that area. And then we're seeing this like electrical activity earlier for the English speakers than Spanish speakers. Like that much is very clear. And then,
Well, because yeah. Go ahead.
so then the question is like, so what does that mean? Like, why do the English listeners have like an earlier, like what are they perceiving in the signal that causes that electrical? Is that the onset of voicing, or is that certain number of like?
Well, you can think of it as a shorter lag between the actual input and what you're doing. But yeah, but you can read the paper. They have behaviorally everything explained. We were mostly interested in comparison with the brain, but
And the model, right?
I think it's like for example, in the tone literature, you can show that FFR is better. So the frequency following response is better at 7 months than 11 months. So it's more clear in resolution, for example, because the brain is probably more attentive, and then you make circuits to attenuate some features that you're not interested. So it actually would be interesting to use your explanatory mechanism to see how this would work, how you're adjusting your various thresholds to get rid of stuff that you have decided, or not that you have decided, but like you've realized that is irrelevant. And then, paying more attention to stuff that is relevant.
I mean, I get that there's a language specific difference in the brainstem, which is super cool.
Right.
But exactly why we see that
Right.
difference, like it's still a little bit unclear to me, like why the languages would develop at the brainstem in exactly the way that they have.
Right. It's interesting.
And can you happen to know if we can rule out like kind of like higher level
Yeah.
other areas of neural activity that are exciting the brainstem, like maybe like a kind of predictive or anticipatory mechanism, or do we want to say?
Well, predictive and then
Too fast.
yeah, predictive. It's too fast. That's the
But it's
main.
also in the context of an experiment where you're hearing this hundreds of times.
True. True. Yeah.
But you should expect.
You
Exactly.
definitely should expect back because you hear it 3,000 times in a row
Yeah.
while watching a silent movie. But I mean, I think there is interferences from the cortex for sure. The idea is that well, it's too early, and then what kind of interference would it be? Would it cancel out with averaging? But maybe if you're repeatedly hearing the same thing, maybe not. Like I'm trying to think like how you could control maximally. And there's other body of work that looks at this, but presumably if it were just cortex that is language irrelevant, right? I mean, what you're saying is that maybe there's downstream, yeah.
So like.
I mean, there must be for sure. Nobody's denying that. But I think the idea is that it's so early that the signal is not coming in yet, and maybe there is no interferences between repetitions.
Yeah, I guess the question is whether it's a difference in the brainstem or whether it's in a difference in the way that kind of, I don't know, maybe left superior temporal gyrus or other areas of the brain are interacting with the brainstem in real time.
Yeah.
That is contributing to this response.
Right.
I don't know.
I mean, in a sense, there's always a problem with trying to localize processing, and if you look at our convolutional models, there's information at several places, so it's likely the case that brain does something similar. Anyway, this is more. I mean, the focus of our work was not CABR, but like more comparison. But I think it's very exciting. Despite the confounds, there's like independent labs are coming with this very interesting set of ideas. But I agree, there are confounds.
Yeah, it's just more to understand.
Right. Okay. So one of the latest things project that I've been excited about is modeling language evolution with these models, because we found something quite surprising that I think illustrates the utility of using these models in the scientific process. What I'm kind of getting at is that the formalist theoretical tradition has come up with a lot of concepts over the decades, and some of which are useful. And as we move in the direction of modeling language with these deep learning approaches, I think it's worth seeing if there's anything symbolic like that we have learned in the formal tradition over the past 50 years that we can use as a descriptive tool or for understanding of how these models do things. And I think there are quite some symbolic level formal approaches that are useful. And this is along those lines. So can we join forces in a sense and use stuff that formalist tradition has learned and try to see how they pan out, or like how they are an epiphenomenon of neural computation, right? So can you get something like, you know, an approximation of merge, which is such an important tradition concept in the formal tradition in these models. And one thing that we were very surprised by is that these models concatenate words spontaneously. So the first phenomenon you observe is spontaneous concatenation. Okay. So what does that tell me? It's very interesting. So it's very peculiar that a model that would only ever see single words would start saying two words, right? You know, in the output. And that's not just like a one-off. It's like a feature. And I think to some degree it has to do with imitation, right? Imitation is a very productive process. And if you're imitating and not just reproducing, like most other deep learning models do, you're allowed to say two words. Because, you know, you're not reproducing, you're trying to approximate what you hear. And one word and two words are still within the approximation space. So we observed that the models are doing this thing where they start putting words together. They were trained on box, water, under, blah, 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 a couple of words. And they started putting them together, even three sometimes. And so we did a bunch of experiments on these models, and we realized another peculiarity, which is they do put words together more in the negative areas of the latent space. So the more negative you go, the more concatenation you do. So that's a peculiarity. And so like, here's an example, you know, you have a latent code, right? You know the latent codes by now, ones and zeros. If instead of with zeros and ones, you generate with fives and zeros, you know what's happening, single words. But if you generate with minus fives or minus tens, you get concatenated words like raggier, suitier, and so on. And one thing that is peculiar is that this concatenation appears to be semi-compositional. What you can find is negative values of the code that represent a single word, right? So when you generate with 0, 0, minus 1.5, 0, 0, 0, 0, you get greasy in the output, one word. When you know, and then you have positive code, like we know that by now. 0, 0, 1, 0, 0 is year, suit, ask, water, and so on. When you force those two together at the same time, you can get predictable outputs, right? You can say, okay, suit is represented with this code. Carry is represented with negative area in this code. When I force the two of them simultaneously, I get a concatenation. So we call this semi-compositional concatenation because it's not, you know, one-to-one mapping, beautiful, clear system yet. But there's definitely traces of compositionality when you can predictably force various outputs that you desire. So greasy, you know, only the third bit in the negative range generates greasy. If you add a positive range, you get water greasy, or you get year greasy, or you get as greasy, or you get suit greasy. And again, these are models that never saw greasy in any way or shape or form other than a law or, you know, any other words. And so there is an interesting hypothesis for how this happened. Now, this is great because for a long time, people have been trying to model evolution from a single call systems to, you know, complex call systems. And every child needs to go from a single word stage into a complex signal or multiple word stage. And of course, language evolution, presumably at some point was more holistic, call meaning a single call meaning pairs, and then it became highly concatenative and combinatorial and compositional. And so we're basically seeing a kind of step of spontaneous concatenation that is semi-compositional, and we can identify a neurally plausible process of how this happened. Now, this is not to say that compositionality evolves due to this process, but it is a testable hypothesis predict. These models can generate testable hypotheses that can also be formalized and kind of brought to the formal world. So we're trying to bring formalism and empirical neural mechanisms. And we call the process disinhibition. So that might be interesting for your work as well. So you in the fully connected layer, you have feature matrices that can be positive and negative, right? So negative feature matrices will attenuate the symbol, and post-rally it'll be at 0. Positive features will excite, and you'll send it forward, and you'll get excitations, and through the convolution layers, you get the point. So there's a simple reason for why concatenation happens. So if you have negative matrices or inhibitory neurons, what do negative latent space values do? They inhibit as well. So if you inhibit inhibition, you get disinhibition. And actually there's work where in speech processing, disinhibition is a well-known thing, especially when you do segmentations. I think it's an important aspect of segmentation. Here we're saying that there could be this very interesting stage where a fully compositional merge or compositional concatenation can arise in the following way. Your inhibitory neurons can start representing single words, as we saw in our model. And then if you inhibit inhibition, so if you do disinhibition, the disinhibition starts representing single words. I should say disinhibition. So you have inhibitory neuron and inhibitory neuron. Together, they disinhibit, so they excite. If that starts representing single words, as we've shown it can, then you can get compositional merge. You force one word in the output, and through disinhibition another, and you get basically a representation, a compositional concatenation. Okay, that was complex. And I'm not saying that this is actually biologically how we go from a single word to multiple word units, but it's a testable hypothesis. And I don't even have ideas how to test this, because it would be very, maybe there are ways, maybe during acquisition, you could see if disinhibition plays a role. There is some evidence, but again, it's like very circumstantial. But the point is that you can bring together something that is exclusively neural. It can take these processes in neural computation. With interpretability techniques, you can understand what's going on. It took a while before we realized, oh, that's why the negative values do inhibition, do concatenation. But you can make testable predictions that are potentially useful, and you can basically show that there are neural mechanisms behind these assumed epiphenomenal symbolic formalisms that we've been working on. And this is very basic, it's not complex syntax yet. There's no movements or phrase structure or X-bar theory yet that we're showing, but some concepts in formalism are useful, others are probably not. And And you can show that there are clear, interpretable neural mechanisms that generate testable hypotheses. Okay, so hopefully in these two classes, I convinced you that we can do a lot with these models, and next two classes will be more hands-on. Stefan will show how to add a parent to the picture, how to add pictures to the picture. And there's a lot of fun actually modeling, because very little work, there's not much innovation and modeling and architectural design choices that academia has now turned into full evaluation, and the industry is creating this model. So it's a lot of fun to create and play with the architecture and try to actually build a model that is realistic and try to stay away from shortcuts that engineers are having. So next two classes will have that, and we have the collab I shared with you. So for those of you who are under credit, you'll play with the code and train a model. But these are all the things you can do. And in the rest 7 minutes, either we do questions and answers, or I can show you how this model was useful in something completely unrelated, which is finding new meanings, new potentially meaningful properties in a completely different communication system, which are that of whales. So do we have any questions? Yes. Okay, option 2, no question. Okay, so I will switch my slides. I will just have to share again. So what we're incidentally building with these models and the interpretability techniques, of course. If you just have a model and you don't have monosemanticity and you don't have a a way to causally show something, then you're it's harder to understand them and harder to use them. But what we're incidentally modeling, creating, is a very smart clusterer, and an extremely smart clusterer. And it can be used in other communication systems. So presumably, right, if language is informative imitation, again, this is a working hypothesis that I still need a lot of thinking about, but maybe other species are doing similar than we are doing, right? They're trying to approximate what they hear from their caregivers, and they need to do so in a way that is informative. And so you can think of sperm whales communication system, which I happen to work on, as encoding decoding problem. And for the longest, this was considered a Morse code. So whales click, they exchange groups of clicks that are called codas. So if you see a whale, I don't know, do they have a video? I don't have a video here, I think, but it'd be like one way, click, 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 another way, click, 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 and they do that in seemingly, meaningful context before they hunt, when they socialize. It's not some sort of mating or birdsong type of system. So people thought, oh, this is like a Morse code. The number of click matters, and you can have codas like click, click, click. You can have codas like click, 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 click. You can have codas like click, 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 click. You can have codas like click, 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 click. You get the point, right? You can have codas like 8, regularly spaced, 8 increasing. So I'm working on Galapagos now. You have codas like click, 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 click. So various rhythmic patterns. And nobody was looking at the spectrum. So we did this. We built a GAN, exact same GAN, but like way higher in dimensions, because these guys have more higher frequencies. Imitate whale codas and do so informatively. Now we know that our GAN model learns phonemes, learns reduplication, learns words, learns meaningful units. The presumption is maybe it'll learn something meaningful and help us. We didn't know. I mean, we went really blind into this. It's like, let's try. And then we developed this thing called that is the same as, take a single neuron or like a single variable and stretch it to extreme values, but we add causal inference on that. So you can directly observe an effect of a single neuron on something that you're interested. So when we tested a few things, and great, the model learned that number of clicks is important. 1 bit basically represents number of clicks. 1 bit represents timing between them per grade. This is all happy, we're validating. And then we were trying a few other things. And like 1 bit actually encodes spectral properties and another spectral regularity or distribution of the spectrum. Excuse me. So that was peculiar. And actually, we get a ton of press for this project, and I was like interviewed by one of the outlets and said, well, our model predicted that spectral properties are important, but we don't really know. So that was at a time where the model already predicted something we didn't know yet. And then before we were looking at a spectrum and found these really interesting patterns. And so we went and checked, and basically, I don't need to say anything about vowels here, but on the surface, these clicks look absolutely nothing like human vowels, and they're even called clicks, which is, is misnomer. But if you think of the production, these are, pulses of their phonic clips, which are exactly the same as our vocal folds. And it's true that it's very hard to see patterns when you look at the raw form, but like the model was suggesting, oh, spectrum is important, spectrum is important. So we were digging and digging and digging. Turns out that if you start removing time between these codas, it's way more easy to observe spectral patterns. And so when you start removing this timing between codas, you then start seeing this really clear, well, spectrums don't project well, but some codas have 2 formants in this range. So you see 2 formants, and some codas have only 1 formant, and they're very discretely distributed. I would play you, maybe I will later, how you can hear the difference with your naked ear. And there are like also patterns that are diphthongal, it's seemingly very controlled, because this is very repetitive. Like you have one pattern where the first click is high and the rest is flat. And several whales do that in some contexts on some longish codas. And so we basically stumble upon this extremely structured, discretely distributed set of formant patterns. And I was very happy to realize that actually, if you look at how this is articulated, I was reading this paper, like how is that, like where are these resonant frequencies coming from? And I realized, oh yeah, it makes perfect sense. They have phonic clips, convergent evolution, nothing to do with our vocal folds, but very similar. And on top of that, they have the so-called distal air sac. And they have to change, 1 centimeter of distal air sac to get the spectral patterns that we're observing. So that's well within their possibility. They're probably moving this giant spermaceti organ back and forth, that's my guess. But the point is that this is basically a source filter production, and presumably this spectral patterns might have some meaning. Our model thought it's meaningful. It doesn't mean it's meaningful, and we haven't found like direct evidence yet. We have some interesting work on some different usage of these vowels. It also happens in Galapagos, in other populations of whales, but the point is that we did have to do a lot of digging to get to these patterns, because first you would think that the entire spectrum matters, but like this just a part of the spectrum. We had to remove timing, otherwise it would be almost impossible to see these patterns. But we did so much digging because our models were predicting, that they're important. And so that's a nice way where you can use these extremely smart clusters for something other than language. Yeah.
So, so-
No. No, you do exactly as in for speech. You throw 3,000 codas at it and ask it learn to imitate and encode information into codas. And a generator needs to learn. It takes a code. It needs to turn it into a coda. They don't.
Don't you give them different codes?
Yeah. I mean, they should know which, just how do they know that different words are distinct?
Yeah, also that seems to assume that the quotas are different, right?
Yes. Well, no. Well, I guess we feed it different coda types, but if you feed it exact same codas, then maybe the model would learn something, it would use some other acoustic properties to encode information, but it has classes. So there's no prompting to learn classes or codas. Just as when they learned words, there were no prompting to learn words. There were different words and it happened to learn them.
You tell it that this word is one word, and it has a different code. So,
No. You never tell it that.
so the code, the same word can have different codes.
No, the same word after learning, one word per code, but there's no pairing. A model has a bunch of codes and a bunch of words. It needs to maximize information between words and codes and automatically matches them. But it could learn anything about other non-meaningful things about speech. But it doesn't because it's a smart cluster. That's what I meant by smart cluster. But there's no intervention on our part. You throw a bunch of words at it. We don't even know how many classes of codas are there, or they're like if they're substructure, right? And there was substructure that we weren't knowing. We were feeding it 1 + 1 + 3 codas of 2 types, but we didn't know there were 2 types. We thought it was just the same type. And then it was a smart cluster. It encoded information because it needed to communicate.
Can you go to the slide where you manipulate the code and infer that the whale language has meanings?
This.
Yeah.
So this is just you take each bit and you see what you take it to extreme values, right? We are used to that now. And you see how the effect disambiguates from the rest of the bits. This is the causal. It's called the causal disentanglement with extreme values. It could be useful for other animal communications. We just didn't. You have elephant vocalizations. You don't know how many classes are there. You don't know what elephants are attentive to. Maybe that can help you. And I'm not guaranteeing that it can help you, but it's a tool that could potentially uncover new types and so on.
That's the first layer, or that's the code?
No, that's a code. Symbolic. We're not even looking at any layers. Yeah.
How many do you start with? How many zeros and ones?
We started with 5. I mean, but it's FIW GAN, so it's a binary code. So in principle, it's 2 to the power of 5 classes.
Oh.
But what we've observed in speech modeling is that this is just a prior. Even if you fail with the estimation of the number of classes, the model will still learn. That's a nice thing.
And for the training data, did you take out, like the first time you ran this, did you take out the pauses between the?
No.
No,
No,
with
no.
it. So it learned
Yeah.
the spectral properties with the pauses in there. and then
Right.
visualization, you
Yes,
just take out the
yeah.
pauses. and
I needed to remove it. It was kind of incidental to something. No, actually, I was cutting down to see if there are any trajectories. I was cutting down silences, and I said, let's get all the silences. And then it was like, oh, the realization was, oh, these are actually discretely distributed. And that was the interesting part. Like if you had some sort of distribution, like who knows what their formats are coming from. But it's like, no, if you're one coda, you're either one type or the other. So that's why also timing was important, removing timing, because initially we remove all the timing and you could start seeing the changes in types that were very discrete. Okay, I think we're way past the hour. Thanks so much. And stay tuned for next week.